Chemical mechanisms are very important when you're studying the kinetics of combustion. My name is Tom Condra and I'm Associate Professor at the Department of Energy Technology, Aalborg University. I'm going to show you how to determine the rate of formation or destruction of components using the Zeldovich mechanism. What we're going to talk about is how to isolate the rate of formation of components in a chemical mechanism. The chemical mechanism we're going to have a look at is the so-called Zeldovich mechanism. The Zeldovich mechanism is a mechanism used to analyze combustion and especially the formation of nitrogen oxide, NO. Nitrogen oxide is a component, a pollutant, which comes especially from diesel engines. So the Zeldovich mechanism looks like this here. It is O plus N2 with the reaction rate K1, NO plus N. Second reaction is N plus O2, rate K2, NO plus O. The third reaction is N plus OH, K3, NO plus hydrogen. Now, what we want to try to find is we want to try to find the DO dt. We want to try to find the rate of formation or destruction of each of these components here over time. This square bracket here that indicates this is concentration. And the units of this are kilomoles per cubic meter. So this one is equal to, if we start off, this is just taking the very first component here, that's O. Now the first reaction here, we're decreasing the concentration of O, so this becomes minus K1. Now we're talking about the law of mass action. So the components, which talk, as I say, the destruction of this, the relevant components are O and N2. So that is the product of the concentration of O multiplied by the concentration of N2. Right, so that's the first reaction. The second reaction, we can see that we're forming O. So this becomes plus K2 multiplied by the concentration of N and O2. So this is N and O2. Let's have a look at the third reaction. There's no O involved. So this is the complete expression. So this is just simply an ordinary differential equation the concentration of O over time, and then given by the K1 and K2 and the concentration of these components here. So let's have a look at the next one, which is N2. So this becomes D N2 dt. So N2, we're decreasing the concentration of N2, so this becomes minus K1, and then we have the concentrations of O and N2 here, O and N2 here. Okay, N2. Now we don't have any N2 in any other reaction, so that one's completed. So now let's have a look at NO. So D NO dt. That one is equal to, we start off in this one here, we are forming NO, so this becomes K1 times O multiplied by N2. K1, concentration of O, and N2. Good. So let's have the next reaction. The next reaction again, that simply says plus K2 N multiplied by O2. And then we have the last reaction, which simply says plus K3 by N multiplied by OH. Good. So we can continue on down, taking each individual component. So just for the sake of, so that we can see what the reaction is again, let's now look at the concentration of N. This one up here. So this becomes D N dt. That one is equal to this is given the first one here, that becomes K1 by O N2. Now in the second reaction we're reducing the amount of N, so this becomes minus K2 N multiplied by O2. And then the last reaction, again we're reducing N, so this becomes minus K3 by N multiplied by OH. So we could continue on taking all the other components. This is N, O2, etc. I think you can sort of see the principle in this one here. So if you're taking all of these equations, if you have a differential equation for each one of them, they're just simply a set of 6. 1, 2, 3, 4, 5, 6, 7 differential equations which are coupled together. And to solve those ones, they're just simply a set of coupled equations. You can use a numerical method, say the Runge-Kutta method. But what we're going to have a look at now is the so-called concept of steady state. The concept of steady state is just simply a little trick that we can use to simplify the expression, that we can maybe, instead of solving all the equations together, that perhaps we can just simplify it and maybe get a simplified expression for one of the components. And here we're especially interested in NO. So let's have a quick look at steady state. So the idea is that we have all of these components together. This is time down here. So if we look at concentration of some component, it doesn't really matter which one it is. So some of the components maybe will start off with this here. And some of them maybe will start off high concentration and lower concentration. Some of them, which involves in particular radicals, they may react extremely quickly. So if we take one of them like this, it might look like this. So this simply means it will react over a very short time, and then the rate, the D concentration, dt, that's equal to 0. So what we do is, let's have a look at the rate of nitrogen with time. So this simply means that this expression up here, we make that simply equal to 0. So then, if we isolate from this expression here n, the concentration of n, we will end up with the following expression here. This becomes K1 by O multiplied by concentration of N2 divided by K2 concentration of O2 multiplied by K3 the concentration of OH. Now, this is just a simplified expression for this one, the concentration of N2. You can see it's only involves K1 and K2. Now, if we then combine this one with our expression for NO, then in actual fact we will end up with the following expression, NO, which was given on the previous page, dt, given on the previous page, and using this expression here, we end up with a very simple expression, K1, or the concentration of O, multiplied by the concentration of N2. So this is a much simpler expression than what was given before, and perhaps this is the one that you're especially interested in looking at. So that was the idea of steady state. I hope you've learned something from this short presentation. If you want to look at some other education examples, just have a look at my YouTube channel. Thank you.